Hi, welcome to the sixth session on holomorphic functions, part of complex analysis. So, the topic of today's session is differentiability of an inverse function. Suppose f is a bijective map from an open set U onto an open set B in C, so that f is holomorphic on U. Then we can talk of the inverse f inverse from B to U. So what is the natural question you would like to ask? What is the natural answer you would like to ask? Say. So whether it is differentiable, right? What is the natural answer? I know. Yes. And what should be the derivative? You already know from your calculus real analysis days. It must be like something like 1 upon the derivative, original derivative, right? Whatever it may mean. We will understand that in a minute. Okay. Very rigorously. So this is very easy to prove. Okay. But the important thing is something I can settle now. If you had watched my videos on continuous arguments, in the third lecture I talked about continuous argument. If I have an open set on which continuous argument exists, if and only if continuous logarithm exists, then I said a continuous argument cannot be a holomorphic function. Because by Cauchy-Riemann we know any real valued holomorphic function must be a constant. We had already seen that. Right? Therefore, there is no question of asking about holomorphicity. But logarithm is a continuous logarithm. If it exists, okay, it's a complex valued function. So I can ask whether it is going to be holomorphic. And then, if so, what is the derivative? Again, you know all the answers based on real analysis. You know what should be the answers. Okay, that's what we plan to do. Okay, we will, if time permits, we will also derive the logarithmic series, log of 1 plus z, right? Where the logarithm should be very carefully defined. Wherever the logarithm is defined, what kind of logarithm we are talking about, etc. We will do that. Okay, but have that idea in mind so that you know what we are up to. Okay, let's get started. Yeah. So I thought it will be a good idea hereafter to give specific references not only to my book, the sections or the theorems which I am going to talk about, so that if you have a copy after this lecture, okay, after watching this, you can also read my book so that you consolidate your understanding and you will become an expert in complex analysis. Okay, so let us start with the result. What do you want? So I have U and V open sets. Open sets. Okay, non-empty of course. And F from U to V is a bijection. And F is holomorphic. Then I want to say F inverse from V to U is holomorphic. And what is the derivative? So this is a theorem. But if you write a theorem, you don't end it with a question mark, right? You should give the answer. But anyway, we will feel, you know the answer, we will fill it in later. Okay. So let us look at. So for sense of using, let G equal to F inverse. Okay. Then what I am going to assume, F is holomorphic, and I am going to further assume, okay, F inverse is continuous. So this is extra assumption. Okay, so let me just mark it, provided F is continuous. So F is holomorphic, F inverse exists, but you have to say F inverse, if F inverse is continuous, then F inverse is holomorphic. Is the result clear? Okay, so how should the theorem, if I want to write carefully, we will write it at the end. Suppose G is F inverse, right? Now let us start, fix a point B in V, right? Therefore it is F of A for a unique A in u, right, and start with any w in v, then w is f of z, right, therefore w minus b, right. So what is that I want to prove? I want to prove g is differentiable, that means g of w minus g of b equal to some g1 of w into w minus b, where g1 is continuous. Okay, this is what we have to prove, right? Okay, now let's look at, see what is w minus b. W minus b is f of z minus f of a, but f is differentiable at a, therefore I know there exists f1, so that is equal to f1 of z into z minus a, right. And what is g of w? That is z, and g of b is a, therefore let's look at this. G of w minus g of b is same as z minus a, right, and this I want to know whether it is g1 times something, g1 times w into w minus b, which is f of z minus f of a. Do all of you agree with that? Yeah. But remember, what is f of this? This is g1 of w, and what is this? F of z is going to be f of z minus f of a is f1 of z into z minus a, right. And remember, that is not, we are taking approach w is not equal to b, and hence z is not equal to a because of bijective nature, right. Therefore g of w minus g of b is g1 of w into f1 of z yeah. This is what I want to do, w minus b, but that's going to be f1 of z into z minus a. Yeah, right. So what are you arriving at? Okay, so let's look at f of z minus f of a equal to f1 of z into z minus a, but that is f1 of z into z minus a is g of w minus g of b, right, and this is w minus a, w minus b. Therefore g of w minus g of b is 1 by f1 of z into w minus b, but this is 1 by f1 of g of w into w minus b. Are you following? Okay, yes. Now this is what is the f1 of g from b to u, b to c. This is continuous at, see, remember g is continuous, right. G is continuous at w, and g of w will be z, therefore this is f1 of z, therefore this is continuous at b, because g is continuous at b, right. Therefore f1 of g composite w, where does it converge to? It converges to f1 of, because the continuity of is converges to b, but that is f1 of a, but is f dash of a. Do you follow that? Therefore what I have got? So plugging in, I have seen, if I write g1 of w minus g of b to be 1 by f1 composite g of w minus b, then this is my g1. G1 is 1 by f1 composite g, right, and this is continuous at b. right? And what is g1 of b? g1 of b is 1 by f1 composite is g at b, but that is 1 by f1 at a, and therefore 1 by f dash a. But 1 by f dash a should make sense. Therefore, what should condition I should put? F dash a is not 0. Yeah. So now let us write down the theorem. Okay. This is a precise statement now. What is it? Let u v be open and C. Okay. Let f from u to v be a bijection. Let a belong to u, right? Let b equal to f of a, and assume 1. F dash a is not equal to 0, and 2. f f inverse is g equal to f inverse is continuous, not a. Okay. Then g is differentiable at b, and g dash b equal to 1 by f dash at a. Go through the proof. See that we used everything. Where did I use f dash a is not equal to 0? At the last time. Where do I use g is continuous ga? Because when I wanted to define g1 equal to 1 upon f composite g, and then I have to use continuity of g. Right, here I used continuity of g at b. Yeah. Sorry, if g is continuous at, here I written a continuous at b. Okay. So do you realize that the proof is very easy, but very deliberately I wrote a very imprecise statement. Roughly what we know is f is a bijection, f inverse exists. If f is differentiable, I want to say f inverse is differentiable. This is a basic intuitive idea. But at this point of time, to get a proof, I had to put extra assumptions. What are the assumptions? My assumptions of f dash at that point is non-zero, and the inverse function is continuous, right? These are the things we have to assume. Okay, please pause, review, proceed. So now we want to give a beautiful application. Yeah, before we go further, let us see, this is some kind of inverse function theorem. If you have gone through inverse function theorem of several variable calculus, that is from Rn to Rn, okay, you know, there you will say the determinant of the derivative at a point is non-zero, then it maps an open set around a onto an open set, and the inverse function is differentiable. Okay, and for that function you also need the function f is continuously differentiable. Okay, right. Whereas here we are going to say something much stronger. This we will prove after open mapping theorem. We are going to see how to relax many the conditions which you have kept in here in the hypothesis, namely f dash a is not 0, and f inverse is continuous, various kinds of stuff, right? Are you following? So later, after a lot of another, perhaps 15 videos or 20 videos, okay, we will prove open mapping theorem, then we will give a much more strengthened version of this theorem. That is what is called inverse function theorem. See, inverse function theorems are very important in various parts of analysis. For example, here you know inverse function theorem, as I said, in calculus of several variables. And here in complex analysis, we are going to have inverse function theorem, which will play an important role. And in functional analysis, you will have bounded inverse theorem. Okay, right? These are all very important results. Why they are important is very interesting. because this is in algebra you won't have such a thing. Okay, this is just to take a slight digression. I'll come to that. These are the things you can learn from me, not necessarily from a book. See, in algebra, if I have two algebraic structures of the same kind, let us say two groups G1 and G2, or two rings R1 and R2, or two modules, or two vector spaces B and W, right? If I have a bijective map which has the correct homomorphism, that is between groups, group homomorphism, between rings, ring homomorphism, between vector spaces, linear homomorphism. Okay, so it's a bijective map which is a correct map of the algebraic objects. Then I have inverse, okay, from the codomain to domain, right? That is automatically a homomorphism of the kind. Are you following what I am saying? These are the things you have to understand, right? If F is from G to H is a group, okay, bijective homomorphism of groups, then F inverse from H to G will be automatically group homomorphism. Similarly, if F from B to W is a linear map which is bijective, then F inverse from W to B will be automatically linear, and so on. But in analysis that doesn't happen. Okay, if you learn topology, if you had also followed some of my lectures, there I would explain again. I have a map of two topological space X and Y. F is a map from X to Y which is a continuous and bijection, but F inverse from Y to X need not be continuous. In fact, we saw an example when we did continuous arguments. Do you remember? Close to 0, open at 2 pi, to unit circle, the map t going to e power it, that is a continuous bijective map. But the inverse cannot be continuous because the circle is compact, whereas the interval which you are talking about, semi-closed interval, that's not compact. It's not even closed. Yeah. And so any kind of theorem in analysis which gives you an idea, just because it's a bijective map with corresponding whatever the mapping property, continuity or differentiability or holomorphicity, that kind of thing, it's very interesting under what conditions the inverse is automatically a map of the correct kind. This may be vague because this kind of thing people don't push into your thing. It's okay. I will give an example. Because many teachers want to give something very simple so that you think you understood completely, so that you will appreciate the teacher, right? Just imagine if your mother and parents decided when you are a baby, just born baby, you don't understand language, whatever the language they speak, be it Marathi or Hindi or Tamil or Kannada or English, okay, they don't understand, so they don't talk to you. That would you learn that language? So one other thing is make it simple and keep repeating. From the context you keep on understanding. This is the golden principle of understanding anything. Okay, but while teaching, many teachers forget that. They think they have to give it very simple so that students will understand, they will feel happy, then they will think I am a great teacher. Okay, but in my opinion, we are doing a disservice. You are capable of understanding better. The only thing is gradually we will keep increasing the standard. If you notice, that's what I have been doing in all my lectures. Okay, this is a digression. If you don't want, skip it. Okay, if you had watched so far, what do you mean by skipping it? Yeah, anyway, right, let's go back. So an application is what I want to give. What is the application? So let us recall, we are done for any alpha real number, we define what is meant by R alpha. R alpha is array complex number z in C star, okay, such that z by mod star is not e power I alpha. So the picture is something like this. This is alpha, this is R alpha, so I remove. Okay, therefore my U alpha was C minus R alpha. This is an open set. Okay, so in one of the continuous arguments videos, we proved the following. Okay, what did you prove? There exists a continuous function theta alpha from alpha to alpha plus 2 pi to u alpha to alpha plus 2 pi. It's a continuous real valued function with what property? For each z in u alpha, z is mod z into e power I theta of alpha of z. Therefore, theta alpha of z is an argument of z. So naturally, it's a continuous argument, because as z varies, the argument I am going to get, namely theta alpha z, that's also varying continuously. That's why we have a continuous argument. This we have proved. Okay. So using this, then we define what is meant by logarithm. Log alpha of z. Okay, log alpha from again u alpha to c, namely start with z and define, maybe I don't remember what is the notation, log alpha of z. This by definition is log ln of mod z plus I time theta alpha of z. What is ln of z? See, mod z is a real number and it is positive, right? Because z is in u alpha is in c star, it is non-zero, therefore it is positive. Therefore ln is the natural logarithm or Napierian logarithm. Okay, we have the ordinary exponential map, exponential of log of mod z is equal to mod z. Okay, we know exponential map from r to r plus, that is 0 infinity. Okay, and it's a bijective continuous, and inverse is log, that is also continuous. So that is what we denote by ln. Okay, ln may be Napierian log or natural log. Okay, so now notice that log alpha is continuous. Why it's continuous? Because z going to mod z, that is from u alpha, which is c, to r, this is continuous, this is actually r plus, and this going to ln to r, this is continuous. Therefore composite, this is function continuous, and by construction theta alpha is continuous, I time theta alpha is continuous, therefore sum of two continuous function, therefore log alpha is continuous, right? Next, remember the thing is it's a bijection. Okay, I have a map. So now what do I want? So let me start with the set. Let me say what is the set alpha. So let me say it's a h alpha to be all complex numbers z and c, so that imaginary part of z, if x equal to I plus y, okay, alpha less than y less than alpha plus 2 pi. So this may be my alpha. So horizontal strip. Right. So let us look at the map h alpha to my u alpha, right? X plus iy going to exponential of x plus iy. Okay. Alright. We know exponential from c to c is holomorphic. Therefore this, its restriction to h alpha is holomorphic, and I claim this is 1 1. Why this is 1 1? Let me just write e power x plus iy. For simplicity, this is e power x into e power iy, right? It's 1 1. Suppose e power x1 plus iy1 equal to e power x2 plus iy2. These are complex numbers, therefore their modulus must be the same. But what is the modulus? Modulus is going to be e power x1 here, and here modulus is going to be e power x2. Right? E power x plus iy is going to be e power x into cos theta plus I sin theta. Right? And therefore the modulus will be e power x, and this will be 1. Right? Now remember, exponential is strictly increasing. Strictly monotonically increasing, therefore it's a 1 1, and hence this implies x1 must be equal to x2. Right? Therefore what do I have? I have e power x1, e power iy1, e power x2, x1, e power iy2, because x1 equal to x2. Right? Therefore this is non-zero, that means e power i1 equal to e power i2. Let me assume y1, y2 are real numbers, therefore y2 is greater than y1. Remember, where are y1, y2? y1, y2 lie in the interval alpha to alpha plus 2 pi. Right? Therefore e power I y2 minus y1 equal to 1. Therefore by periodicity y1 minus y2 equal to some 2n pi. Remember, this is positive, therefore my natural number n must be natural number, y1 minus y2 minus y1. Yeah. Therefore in particular this must be greater than 2 pi, greater than or equal to 2 pi. Yeah. But where does y2 minus y1 lie? Okay. y2 minus y1, y2 is less than alpha plus 2 pi, and y1 is greater than alpha, therefore minus y1 is strictly less than minus alpha equal to 2 pi. Therefore y2 minus y1 is strictly less than 2 pi, but it must be greater than or equal to 2 pi. This is a contradiction. Therefore y1 equal to y2. Okay. If so I should assume, suppose I assume if y1 is not equal to y2, assume y2 is strictly greater than y1, and I get a proof. Yeah. So we have proved this map is 1 1. Okay. Let me call this map as f from h alpha to u alpha z going to exponential of z. Okay. This is 1 1 on h alpha. Right? And it's a bijection, it's on to. Why? Start with any w in c alpha, u alpha, right? Then w by mod w. Remember, u alpha is in c star. Therefore this makes sense, this is not equal to e power I alpha. Right? Therefore we know there exists a, remember what is our thing, therefore w is going to be mod w into e power I theta alpha of w. Okay. And where does theta alpha of w makes sense? It lives in alpha to alpha plus 2 pi. Therefore it's on to. Okay. So this map you have from h alpha to u alpha is bijective and holomorphic. Is that clear? So pause, review, proceed. So now what is G? F inverse. This is our log alpha. Why? Because that's what we found out. Yeah. What is log alpha? Log alpha of any z, okay, is going to be ln of mod z plus I times theta alpha of z. Therefore exponential of that is exponential of this is going to be exponential of log of mod z is going to be e power log of mod z into e power I theta alpha of z, but that's by definition is mod z into e power I theta alpha of z, which is equal to z. Right? Therefore this is the inverse. Okay, pause, review, proceed. Make sure you understand. See, some of the things are very easy. Many times, you kind of just because of gut feeling, you assume. Teachers are also somewhat, if at all they do, most often what I am doing is never done. Okay, if at all it's done, they will keep on writing, you think it's obvious. But you should learn from the very definition how to check all these things. Okay, we have done that. Now we also know log alpha is continuous. We already said this is continuous. Therefore, log alpha is holomorphic on u alpha. This is by the theorem. Yeah. So this is what I said in the continuous argument. I already proved there itself its log alpha is continuous inverse, but it's actually can be proved to be holomorphic. We have proved it now. Are you sure we understood all those things? Very good. Now how can I use holomorphicity? Again, make sure that you did everything. Okay, because what did we say? F dash a should be not equal to 0 is one of the conditions. Here, what is the map? It is exponential map from u alpha to h alpha to u alpha, right? Therefore, if my z is exponential of w, right, then what is a exponential prime at w? It's exponential of w itself, which is non-zero, right? Therefore, the hypothesis of the theorem are checked. The derivative is non-zero and the inverse function is continuous. Have we checked all those things? Therefore, I can apply the theorem. Yeah. Therefore, I concluded log alpha is holomorphic. Isn't it good? Okay. Now, what is the next question? What is the derivative? Derivative you already know. By the last theorem, we know the derivative is log alpha dash at any z equal to what? That's what we want to do, right? But remember, if that is nothing other than, suppose z is e power w, right? That is my f of w is z, right? That is g of z is w. Therefore, g dash at z is 1 by f dash at w, right? You follow that? So 1 by f dash at w is what? 1 by f is f of w. Therefore, f dash w is e power w. But that is 1 by z. Therefore, okay, derivative of log alpha is 1 by z. Okay. Do you agree with that? Isn't it nice? This is exactly similar to what you have seen in real analysis. Yeah. The derivative of logarithm is log x is 1 by x. Right? You got it. Good. So just make sure you follow this. Next, what I want to do is I want to get the power series expansion for log. You may recall in real analysis, okay, log of 1 plus x is going to be, I may write it wrongly, but just to make sure I am writing it correctly, n greater than equal to n equal to 1 to infinity, right? So I want to know, notice that when this has to be continuous, this has to be continuous, meaning mod x has to be less than 1, because remember, when x equal to minus 1 is 0, therefore it's likely to be valid only when x is greater than minus 1, right? And whereas look at this power series by ratio test, the radius of convergence is going to be x power n plus 1 by n plus 1 n by mod x power n, therefore, okay, which converges to mod x. Therefore, when mod x is less than 1, this series is convergent. Therefore, this is valid for minus 1 to plus 1. Yeah, right. Now I want to know whether there is such a thing. So what should I expect? So let us look at. So I want around 1, right? Therefore this is my 1 in the complex plane. Therefore I have how much I can go. So I want to look at, let me put 1. This looks too far away for me. So let us look at the open ball B11. So set of all complex numbers z so that mod z minus 1 is less than 1. So the boundary is of course not included, right? So now this is a set. Remember, if I want to talk about logarithm, okay, then I have to choose the so-called branch carefully. That makes sense only on subsets of open sets of the form u alpha for some alpha, right? So what should be the alpha I can choose for this? That is, I want to say this b11 is contained in some u alpha. What is the natural choice of alpha? I can choose alpha to be pi by 2, or alpha choose alpha to be pi, or I can choose alpha to be 3 pi by 2 also, or any other alpha for that matter. I can choose any one of these guys. Okay, I cannot choose these guys because this will be there. Are you following? See, you should always try to understand it. I can simply say look at this logarithm and you will simply accept, but you should also try to learn on your own. So the obvious choice for me is going to be log of pi. That is, I am omitting my u alpha is going to be this. Okay, this is omitted. Okay, this is my u alpha. These things are all included. Yeah. So I am going to say log pi of 1 plus z equal to exactly the same formula, minus 1 by n z power n by n as n is greater than equal to 2 on b1 1. Okay, this is the theorem if you want. Now I already explained by this power series has a radius of convergence 1 by ratio test, right? Okay, now this, remember, as z where is 1 plus z, this okay, z where is on b11, 1 plus z lies in b11, yeah, and therefore the whole thing lies in thing. Okay, this is contained in 1 plus z lies in u pi. Okay, that's more than enough for me. I don't care whether it lies here or not. One can work out, but I don't want to say that. Okay, this is of course not true, because if I take m1 half, that will be 1.5. That will not, that may, yeah, it's okay. Yeah, let's not worry about it. So 1 plus z lies in, right? Now I want to prove these two are equal. Where? On this open set. Remember b11. So whenever you use calculus, or you can talk about differentiability, and I want to show two functions are equal, what is the natural trick you should use? Look at f minus g. That means f minus g is 0. That means f minus g is a constant. Therefore you know what I have to do, right? The derivative f dash equal to the derivative d dash, right? Then it will be locally constant. But remember, all of you know that b11, any open disk is connected, right? Therefore it will be a constant. Okay, I am just jumping ahead, but you should know. Okay, now derivative of, so let f equal to log pi, then derivative f dash is 1 by, if you want to write f dash z equal to 1 by z. Okay, oh, see, sorry, log pi 1 plus z, therefore derivative is 1 by 1 plus z. Yeah, okay. Now what is the derivative? Let g equal to summation n equal to 1 to infinity minus 1 to the power n minus 1 z power n by n. And this is the radius of convergence. We know, therefore it's a differentiable, in fact infinitely differentiable. The derivative got by term wise differentiation. Therefore what is g dash z? g dash z is going to be minus 1 when n equal to 1, okay, n into z to the power n minus 1 by n when n equal to 1. This is going to be summation minus 1 to the power n z to the power n is 0 to infinity now, right? But this is going to be 1 by 1 plus z. This is a geometric series which is 1 by 1 plus z. So what do you think I have proved? I have proved f dash equal to g dash on b1 1, right? Therefore f minus g dash is 0 or f minus g is a locally constant function. But since f any disk, in particular this is connected, f minus g is a constant. Okay, but what is that we want to prove? F equal to g. Therefore I want to say the constant is 0. So how will I do that? Evaluate it at some point, right? So what is f of 0? F of 0 is log pi of 1 plus 0, which is 0. Yeah, remember, log pi on any positive real number, suppose let me say a is a positive real number. What is this? This is ln of a. Go back to the definition. Yeah, right. So there I am going to do minus pi to plus pi open. Therefore what is the argument? Argument pi will takes values of any z, will take values where? In minus pi to plus pi. Remember? Sorry, pi to 3 pi, right? Yeah. Therefore it will have 2 pi. Yeah. Therefore argument of a will be theta alpha of a will be 2 pi. Yes. Therefore log pi of a will be ln of a mod a plus I times theta alpha of a, which is 2 pi. Yeah. Therefore this. Yeah. So I want it to be 0. So let me just make sure I'm making some mistake. So because what is theta alpha? Theta alpha should take values from alpha to alpha plus 2 pi. Therefore it will take values from pi to 3 pi. But it will be good if it takes values from minus pi to plus pi. Therefore it will be 0. Right, minus pi to plus pi, that will be, okay, I have to say minus pi, okay. So it may be a good idea, there's minus pi to plus pi, therefore I should ask is minus pi. Yeah, so that is going to be this. Okay, so take alpha to be minus pi, not, so just a small correction. So let us look at log of minus pi, where alpha is minus pi. Therefore argument alpha will takes values from alpha to alpha plus 2 pi. Therefore it's going to be pi to 3 pi. But now it's if it is minus pi, it will take minus pi to plus pi, right? Therefore, so this, instead of this I am going this way, that's all. Okay, think of it this way. Therefore the only value will be 0 here. Okay, therefore theta alpha of a, for a positive, theta alpha of a will be 0. Therefore ln of 1, sorry, log minus pi of 1 will be ln of 1 plus I times theta alpha of 1, which is 0 plus I 0, which is 0, right? And what is g of 0? g of 0 is minus 1 to the, say, 1 to infinity minus 1 to the power n minus 1 z to the power n by n. Okay, right, which is 0. Therefore f of 0 equal to g of 0. Therefore f equal f minus g is a constant. That constant is 0. Therefore f equal to g. Yeah, so please go through this. Yeah. Pause. Now did you see that my natural inclination was to take the negative x-axis, so I assumed pi, but later when I wanted to rigorously prove, okay, f of 0 is also 0, that is logarithm of 1 plus 0, that is logarithm of 1 is actually 0. Okay, I have to contend with theta alpha, because we define log alpha to be using theta alpha also, right? There I found I ran into a problem. It's a 2 pi. So what did I do? I came back and corrected. You see that? This is what you have to do. Okay, you should not be ashamed. Now you understand. There is a natural thing, but you know how to surmount because you want to prove certain thing. Yeah, I hope you enjoyed this. Take care. We will meet again.